Hi, everyone. Welcome to Chapter 6, Part 1. So today we're going to start talking about the normal curve, and we'll get into z-scores and spend a lot of time in z-scores in the next video. This is a really pivotal part of the course. We need to understand what's going on with this z-score and how the z-score is related to this normal curve that we're going to discuss first. So let's take it one step at a time. We're going to talk about the normal curve first, the property of the shape, and then proportions. We're going to talk about that in just a minute. And then we'll get into ideas of z-score mainly in the next video, but we're going to try and start talking about it in this video. So let's go ahead and ask a question. Let's say that I got a histogram, a distribution. Let's say that it's perfectly symmetrical. What percentage of the scores are above the mean in a perfectly symmetrical distribution? 50%. So 50% are above, 50% are below. Now you're like, oh, but what about right on? No, don't worry about that. Don't worry about that right now. Let's just imagine a curve, right? Imagine a curve, and if you put a line right in the middle, 50% of the scores are right above it, 50% are below it, okay? This is an important part. If it's really, really a symmetrical curve, absolutely symmetrical, and I'll try and draw one right now, and I'm sure I won't get it very symmetrical. Pretend that's symmetrical. If we drew a line right down the middle, then 50% would be on the right of it, and 50% would be on the left of it. Okay? And the score right in the middle would be, let's go ahead, move ahead on this one, the mean, the median, and the mode. So, in a normal curve is a theoretical symmetrical distribution. So this is kind of important because when we talk about a normal curve, it's basically the same as a perfectly symmetrical histogram. Remember how we made a histogram and then I made this little curve thing above the histogram? When I did that, we were talking about how histograms are basically curves. Now I know this is ugly. I'll show you a better picture in just a minute. But basically it's like a histogram. And we said that if it was unimodal, there's only one bump, right? There's only one mode. If it was unimodal and symmetrical, that the mean, the median, and the mode would be exactly the same place. Okay? That sounds familiar, right? The mean, median, and mode are right in the middle. Okay. Now, what we're going to do is we're going to expand this and say, what if we had like an infinite symmetrical unimodal histogram, right? What if it was not just, 34 people, but it was, an infinite number of people? If it was an infinite number of people, then the mean, the median, the mode would still stay the same. And 50% of the scores would be above the mean, and 50% of the scores would be below the mean. The normal curve is used as a theoretical construct to approximate, ideas of a population. Now, what you need to know, you don't really need to worry about too much of the theoretical background and like how to calculate the normal curve. You can actually calculate the curve and all that stuff. But what we need to understand is that we use this curve to understand what we think is happening in a population when we don't know what's going on in a population, okay? The idea is if we would get an infinite number, then we would have a normal distribution. We would have a normal curve, a bell curve. All right, so we need to show you what a normal curve looks like. This is actually what a normal curve looks like. This is a good normal curve, and we'll get to the percentages in just a minute. But what you'll see is that this is perfectly symmetrical, right? It's unimodal. That means right in the middle, we have the unimodal. And this right here, this dashed line, is the mean, the median, and the mode. The mean, the median, and the mode. So if that is the case, and we have an infinite number of people here. So the y-axis, instead of worrying about it being the exact frequency, instead of using the word frequency, we actually use the word density. Because we're talking about a theoretical density now. A theoretical density, like a proportion, right? That kind of a thing. So instead of the actual frequency, we're worried now about something called a density, which is essentially like a frequency, only like infinite. That's what you need to worry about with that. Okay, now, if that's the case, then 50% of the scores are on the left, 50% of the scores are on the right of the mean, which is right in the middle. Now, if that's the case, the normal curve, besides just having 50% on one and 50% on the other, it also has a specific shape. You've heard of the idea of a bell curve, right? This has a specific shape so that not only do we know that 50% are above and 50% are below, we also know that there are proportions inside of it. And we'll get to that in just a minute. These right here are standard deviations. Standard deviations. Now, for a population, remember, the standard deviation, we don't call it SD or just S. We call that lowercase sigma. Okay? So these right here you see are standard deviations. And in a normal curve, we not only know that 50% are above the mean and 50% are below the mean, but we know that 34.13% are between the mean and one standard deviation above the mean. We know that. Based off of the normal curve, we know that. We also know that 34.13% are between the mean and one standard deviation below the mean. So when you see 1 right here, that is one standard deviation above the mean. And you see -1, negative just means below the mean. So in this case, that is one standard deviation below the mean, right there. Okay? Since we know that 34.13% are exactly one standard deviation above the mean, and 34.13% are exactly one standard deviation below the mean, we know that 68.26% of this distribution, so 68.2% of 26% of all of the scores are between one standard deviation below and one standard deviation above the mean. The normal curve is a special kind of symmetrical distribution that is unimodal and has a specific shape, right? We also know that we can keep going on these standard deviations. We can say that we have between two standard deviations below and two standard deviations above, 95.44% of all the scores are between two standard deviations below and two standard deviations above. Now remember that the entire purpose of what we've been doing is to figure out how strange is Ricky Martin. You remember how we did that, right? We wanted to see how strange is Ricky Martin. How weird is he? How strange is he compared to the others? Well, instead of worrying about his exact scores in terms of years of tenure in Menudo, we can look at his standard deviation. And if we know the curvature of the distribution, if it's normal at least, we can figure out what percentage of the population should be above or below based off of his standard deviation score. Now, one problem that we have, let's go ahead and go to those data. So let's go ahead and look at the Menudo data that we were looking at before. And if you remember, here's our raw data of all of our people, okay? And we are going to be looking at tenure here. So tenure just means how long they were in the band. So let's go ahead. I'm going to freeze these panes in a different spot so we can look at Ricky Martin one more time. The problem with this particular one is that this is not a normal curve. This population is so small that we know that this is not a normal curve. We've already seen that this is a slightly skewed curve. And I'll show you what I mean in just a second. So remember what our main goal was to figure out if Ricky Martin, and he's number 14, there he is, if Ricky Martin is strange, okay? He was in the band for 5 years, so this is in years. The deviation from the mean is 1.44. That means that he is 1.44 years above the mean. I know it's above the mean because this is a positive deviation, okay? Now, if we look down here at the standard deviation is, where did we put the standard deviation? The standard deviation is, let's go ahead and calculate this again. We did their deviation. Let's go ahead, we got the sum of squares. So what we do for the population to get the variance is we take the sum of squares divided by n. And n in this case is 34. There it is right there. Okay. So that is the variance. And this is, I only divided by n because this is the variance of the population. Right? So that's going to be the variance. And then this is going to be lowercase sigma because this is going to be the standard deviation of the whole population. So this is going to be the square root of the variance, 2.40. Okay? So the standard amount of deviation from the mean, so the standard number of years that is the like normal standard of deviation from the mean is 2.40 years. Okay, 2.40 years. Ricky Martin had 1.4, where is he? There he is. Ricky Martin had a deviation of 1.44 years. So his deviation is less than the standard deviation. But what if we want to compare things that are very different from each other, right? What if instead of talking about this in years, which is exactly what we've been doing, right? This is, he's 1.44 years above, he deviates 1.44 years from the mean. The standard amount of deviation is 2.40 years above the mean. What we do instead is we get something called a Z-score. And what the Z-score does is it takes Ricky Martin's score, let's move him over, Ricky Martin's score, right? And looks at it instead of in years, looks at it in standard deviations. So follow me on this one. We are going to look now, let's go ahead and go back to the to these data. We're going to calculate something called a Z-score. And a Z-score is going to look at Ricky Martin's strangeness, how strange he is from the mean. But instead of looking at it in years, we're going to look at it in standard deviations. You follow me on this? So we're going to translate his score out of years into what's called a standardized measurement, a standardized score, which is standard, the standard deviation. The Z-score is going to be the number of standard deviations Ricky Martin's score is away from the mean, instead of the number of years Ricky Martin's score is away from the mean. And the reason why we're going to do this is because when we're talking about the normal curve, if we know the number of standard deviations and if it's a normal distribution, then we would be able to tell not just 50% above and 50% below, but we can tell proportions in between and all sorts of cool stuff with the normal curve. Now, a huge asterisk on this whole thing is that this does assume that the distribution of the population would be normal. And we already know in Menudo, that's just not the case. So we'll talk about what that means in just a minute. But that is an assumption that is made in what we're doing from here on out. So what we need to do is we need to figure out the Z-score. Now you have as many Z-scores as you have people in your sample or in your population, okay? You have n number of Z-scores. So each person gets their own Z-score. And all it is, look at this, x minus mu. Hey, have we already done that already? X is their score minus mu, that's the mean. This top thing above it, that's the deviation. So all we're going to do is we're going to take that deviation, we're going to divide it by the standard deviation. And that'll tell us how many deviations away Ricky Martin is from the mean. So let's go ahead and take a look at this. Now, for the population, we're just using these parameters. We got the mu and lowercase sigma, the mean, and the standard deviation. In the sample, we use x bar, and S, right? Making sure that we have calculated the sample standard deviation correctly when the variance is divided by n minus 1 instead of just n. Remember, we talked about that last time. So let's go back to the Ricky Martin data. All right, to find Ricky Martin's z-score, remember, each person gets their own z-score. So Ricky Martin had 5 years in Menudo. The average for the whole population was, so this is mu right here, 3.558, which is 3.56 essentially, right? So he is where'd you go, Ricky Martin? There you are. 1.44 years above the mean. So this is the deviation, okay? This is x minus mu. X is 5, mu is the mean right here, 3.558882, whatever it is, okay, 3.56. So the number that you see right here, the deviation, is the number of years he is above the mean. That's all it is. In order for us to find his z-score, so let's go ahead and make a new column. And the column is going to be z-score. I better make it a lot bigger than this. All right. The column is going to be z-score. We'll make it a little bit wider as well. Each person gets their own z-score. So I'm going to move this over, because what we're going to do is we're going to take the deviation, that's the x minus mu that we already did. We're going to divide it by the standard deviation. So Ricky Martin's z-score is the deviation divided by the standard deviation. All right? So it's his deviation divided by the standard deviation. And what I'm going to do is I'm going to make sure that we don't do a separate standard deviation. So Ricky Martin's z-score is 0.599. Come back, z-scores. There you are. Let's make these bigger so that everybody can see them. Make the whole thing large so that you can see what I'm seeing. Excel wants to panic right now. Okay. So what we're doing is I'm making this bigger. Make it bigger. There it is. So there's Ricky Martin. I'll put him closer to the top so that we can make sure we can see everything. Okay. So let's take a look at all the information we have about Ricky Martin. Ricky Martin had an average, had a tenure of 5 years. That's X. Okay. The average for the mean for the entire population, mu, that is 3.5, what is it again? I keep saying 3.558, which is 3.56. Okay, 3.56. That means that he deviates 1.44 years above the mean. We squared that deviation in order to find the sum of squares. But his z-score, what you see right here, 0.599, which rounds to 0.56. Okay. His z-score, excuse me, 0.6, not 0.56. His z-score is that he is 0.6 standard deviations above the mean. All right. His score, his deviation right here, where we said he's 1.44 years above the mean. If we look at that in standard deviations, 1.44 years above the mean, that is 0.6 standard deviations above the mean. It is 0.6, it's 60% of 2.403 years. All right, 1.44 is 60% of 2.40. We are changing Ricky Martin's raw score to a deviation, and then his individual score to a standard deviation. The z-score is the number of standard deviations Ricky Martin is above or below the mean. So let's do this for everybody else. So let's get everybody's z-scores. So if you look right here, we're going to get everybody's z-scores. I got to get everybody else down here as well. Okay, now we have every person's z-score. And the z-score is the number of standard deviations that person is above or below the mean. So Ricky Martin is 0.6 standard deviations above the mean. Raymond Acevedo is negative 0.23 standard deviations, which means 0.23 standard deviations below the mean. Negative means below the mean. Positive means above the mean. That's all that is. All right? Now, the reason why we're doing this is so that we can compare it to the standard deviation, compare it to a normal curve and figure out proportions and other things like that. A z-score is standardized. So if I want to know, what is Ricky Martin's relationship to, how is he above or below the mean, I can just look at his z-score and say he's 0.6 standard deviations above the mean. I don't have to worry about whether that's in years or in months or in weeks. That's not what we're saying, right? So I don't have to worry about that. I know that 0.6 is his relationship to everybody else. He is a 0.6, 60% of one standard deviation above the mean. His z-score is 0.60. All right, here's what I want to do then. I want you to calculate for me. I want you to calculate for me participant 1's z-score for liking for donuts. I want you to calculate for me participant 1's z-score for liking for donuts. All right, so go ahead and calculate that now. Okay, so what we need to do when we're looking at participant 1's z-score for liking for donuts, let's go ahead and make sure that we're all clear on what's happening here. So this is participant 1. Participant 1 said they like donuts at a 3. All right. The mean liking for donuts, this is X bar because now we're working with a sample, is 5.43. All right. That means that participant 1 is below the mean. Well, how much? Well, participant 1 deviates negative 2.4286. Participant 1 is 2.43 liking units below the mean of liking for donuts. That's the deviation. Okay. When we calculated, let's go ahead and move these over now since we're working with the deviation. Go back. When we square all the deviations, we add them up, we get the sum of squares. So this right here, 49.714, is the sum of squares for all 7 people. Okay. Now we want to get the variance. So I'm going to put the variance. Let's just put it right here. This is going to equal the variance. Okay, so the variance is going to be the sum of squares divided by n? No, divided by n minus 1 because this is a sample. So divided by 6 is what we've done before, 8.29. And then to get standard deviation, I just take the square root of the variance. 2.87. So the normal amount that people vary from the mean, at least for liking for donuts, is 2.88. 2.88. All right? So how strange is participant number 1? Well, we can already see that that this person is less than 1 standard deviation, right? Because negative 2.42, right? We can tell that's different. But how much, right? What is the z-score? So to do this, let's get the z-score. So the z-score is going to be the deviation divided by the standard deviation. The deviation divided by the standard deviation. And when we do that, we get negative, can't see this very well, sorry, negative 0.84. Make this bigger. Negative 0.84. That means that participant 1 is 0.84 standard deviations below the mean. Their liking for donuts is 0.84 standard deviations below the mean. That's what that means. Now here's everybody's standard deviation. Everybody's z-score, right? Everybody's deviation in standard deviations. Okay, you'll see then that this person, let's go ahead and go with participant number 4. Let's look at participant number 4. If we go back to the raw data, look over here at the raw data, they like donuts at a 9. The average is 5.43. Well, that means that their liking deviates from the mean. How much? It deviates 3.57 liking units, but we can look at this in terms of standard deviations. That is 1.24 standard deviations. Participant 4 z-score is 1.24. They like donuts 1.24 standard deviations above the mean. Now, why would we do that? Because now we can think about things in terms of standard deviations. So we can talk about participant 1's liking for donuts and Ricky Martin's tenure in Menudo in the same standardized way. We don't have to worry about if we're talking about years or weeks or months, whether or not the liking is between 0 and 10 or 0 and 100. We don't have to worry about that stuff. We standardized it now. Now we're talking about it in terms of z-scores. So Ricky Martin's z-score for tenure was 0.6. Participant 1's z-score for liking for donuts is negative 0.84. We understand where that fits on a normal distribution because it's in standard deviations instead of worrying about the individual unstandardized scores, years, months, etc. All right, one last thing, and then we are done. So, how many z-scores are in a distribution? N number of z-scores. N number of z-scores, that's how many are in a normal distribution. All right, you have as many z-scores as you have distributions. That's what you need to know. Okay, thanks everybody.